Welcome to Huawei eLearning Services. My name is Klaus Schweiger and today I will talk about SDN architecture and ecosystem. In traditional networks, most of the network devices are network functionalities implemented in a dedicated appliance like a switch, a firewall or a router. With software-defined networking, operators' network architecture now will change significantly. After completing this course, you will be able to understand the principles of software-defined networking, to describe the 3 layers of SDN architecture, to understand the SDN value proposition, and to understand the SDN community and its standardization organizations. We will start with an overview about software-defined networking. First subchapter is about the evolution on the field of computing and networking. Let's start with a look at the evolution in computer design. Traditional mainframe architecture are big block computers used primarily by large organizations or computationally intensive operations. They consist of a central, mostly very expensive but powerful hardware, a professional, often a proprietary operating system, and on top of that, many different proprietary applications. In this context, mainframe stands for a proprietary system with an enclosing interface, a slow innovation speed, and typically small-scale industries. If you compare this with PCs, then you see that the architecture has strongly changed and is quite different from a mainframe. In general, it is much more modular. A PC provides open interfaces between its building blocks. Between hardware containing the CPU and the OS, you may have, for instance, a PCI or a SATA interface. Between the OS and the applications, you may have an OpenGL, a DirectX interface, or any other kind of interface. This architecture provides, as I already said, open interfaces. And from this aspect, you can derive several advantages. A rapid innovation speed for new services or applications, and of course, it can be used in large industries. Let's remember the evolutionary step from a mainframe to a PC, and let's compare this with the evolution on the field of networking. Traditional networks are complex and quite difficult to manage. These networks have many different kinds of equipment, from routers, switches, to firewalls, network address translators, intrusion detection systems, and so on. Obviously, these devices use different hardware platforms, and they also use distributed control plane architecture, which is typically closed and proprietary to finally provide complex professional features. The implemented hardware and software undergoes years of standardization and interoperability testing. Network administrators typically configure individual network devices using configuration interfaces that vary across vendors and vary even within the same vendor. And although some network management tools offer a central point for configuring the network, these systems still operate at the level of individual protocols, mechanisms, and configuration interfaces. This central mode of operation has slowed down innovation pace, has increased complexity, and has inflated both the CAPEX and the OPEX for running such a network. In future networks, we will see a similar approach as already happened on the field of computing. New systems will provide open interfaces in between the hardware and the control plane, and there will be also open interfaces in between the control plane and the application. And again, this open interface architecture simplifies the integration of new applications, and so this evolution will speed up the pace of innovation. Now we will talk about the problems service providers will be faced with. If running traditional networks, the following challenges and problems may occur. The network can be congested at one section and may be underutilized at another section. Or the network devices are complex. Or operation and maintenance is often quite time-consuming and can be difficult and complex. And the provisioning of new services is relatively slow. This slide shall highlight the network congestion problem of traditional networks. Traffic from router A to router B will take based on the shortest path first algorithm, the direct link between A and B. This can lead to congestion, as shown in red color in this picture. Whereas the link from A to B via C, shown in green color here, is maybe underutilized. Even though MPLS-TE has been introduced to solve underutilized link usage, but most of MPLS-TE planning are pre-configured and does not solve real-time or sudden burst traffic, hence causing network congestion. Now let's take into account some service requirements. For example, there are 3 tunnels to be established in sequence. All links are providing 10 gigabit in here. First tunnel requirement needs a 6 gigabit connection from A to E. After calculation or explicit configuration, it might take the path A, B, C, D to E. Second tunnel with a requirement of 4 gigabits shall go from C to G. Here we take the direct path from C to G, as shown in the picture here. A third tunnel shall be set up between C and D with a requirement of 8 gigabits. This tunnel cannot be set up due to insufficient bandwidth, as you can see here. Whereas if we would use a global view, see the drawing on the right-hand side, we could set up all the 3 tunnels because we would use for the first tunnel the alternative path from A to E via F, G and H. This would provide enough bandwidth to also set up the tunnel 2 and the tunnel 3. This slide now shall highlight the problem of complex network devices in traditional networks. For traditional distributed networks, many control plane protocols have been deployed and need to be configured for the devices, including IGP protocols, BGP protocol, MPLS, IPv6 protocols, and so on. IETF has introduced thousands of RFCs already, and still new protocols and standards are released almost every day. This means that a network expert has to learn complex technologies and needs to keep this knowledge updated to do operation and maintenance in such a network. On the other hand, some vendors may deploy proprietary solutions and protocols. This causes some further difficulties for operation and maintenance processes. Also, different vendors of network devices such as Huawei, Cisco or Juniper, they provide different graphical user interfaces, causing network engineers to learn on multi-vendor environments to operate the network devices. Also, the network experts need to know thousands of commands to be able to configure network devices and to perform O&M tasks. This slide shall highlight the problem of difficulty to perform O&M tasks in traditional networks. Here, as an example, we want to provide a layer 3 VPN for an enterprise, especially on the provider edge router called PE. There is a lot of configuration which needs to be done, like IGP protocols, MPLS configuration, VPN configuration, and configuration of the link between the CE and the PE. This screenshot just shows some of the configuration steps which need to be done on the provider edge device to configure layer 3 VPN for one enterprise. So just this is more than 50 configuration steps. So as you can see, it really can get complicated and complex to do O&M configuration in a traditional network. Now here we want to highlight the problem of slow service provisioning in traditional networks. First, there's a requirement which is defined by a group of experts. Then maybe years later, there will be a standard released which is specifying the requirement. Another year later, maybe, the vendors can offer equipment which is supporting these requested new features. And again, 1 year later, large-scale deployments for the initial requirement may start. Of course, this timescale shown here cannot be seen too fixed, but a time range of 3 to 5 years until a new innovative requirement or idea becomes reality in a network is unfortunately not a worst-case scenario. This is reality in traditional networks. Let's talk about the principles of this new software-defined networking architecture. Let's again start with traditional networks. They are using distributed architecture for the network elements. Let's explain what does distributed architecture mean. The internal architecture of a network device has three planes of operation. Management plane, which handles external user interaction and administrative tasks like authentication or configuration via web interface or CLI. The control plane, which administers the internal device operations, providing the instructions to forward the packets. It also runs routing and switching protocols and feeds operational data back to the management plane. And the data plane, which forwards the packets through the device using the forwarding table supplied by the control plane. And in traditional networks, these three mentioned planes, data, control, and management plane, are provided distributed for each network element. Due to reliability and high availability, the current network are based on distributed network approach, where each device calculates and configured independently and administratively. For example, imagine a traffic entering from provider edge A and exits on provider edge B. When PEA receives the traffic, PEA will check according to routing table. Based on routing table, it decides that in order to reach PEB, it has to go through PEC as next hop. Then PEA forwards the traffic to PEC. PEC does exactly the same thing as PEA, check routing table, finding the next hop, and forwards that to PEB. This forwarding manner is called per hop forwarding. Information inside the routing table are collected and built through static routing or dynamic routing. In large-scale network, normally routers are running dynamic routing protocols such as OSPF or ISIS. Every router in this routing domain collects link state information and then performs independently by using the same routing algorithm, for example, shortest path first to find the shortest route. This network is called distributed network. SDN, or software-defined networking, is a new approach where physically separate control plane and data plane into two different hardware. Now, the software-defined networking architecture introduced by the Clean Slate project of Stanford University is providing a complete new networking approach. In this approach, we separate physically the control plane from the data plane. For this purpose, SDN also introduces a new component called SDN controller. This device now is able to manage several devices in a centralized way. And for the future, new applications or services can be deployed by this architecture via just reprogramming the SDN controller over open APIs, application program interfaces. So customer requirements can be met much more quick. Because it's really essential, we see here again the three major characteristics of SDN. Separation of data plane, sometimes called forwarding plane, and control plane. Centralized networking approach in terms of control plane functionality, and open interfaces in between the networking devices and the controller, and also in between the controller and the application. SDN was initially driven and developed by the Clean Slate program of Stanford University. The Clean Slate program was an interdisciplinary research program at Stanford University which considered how the Internet could be redesigned with a clean slate. This means without the accumulated complexity of existing systems, but using the experience gained over the last decades. The Clean Slate program is closely connected with three names: Nick McKeon, Martin Casado, and Scott Schenker. All three of them have been essential for the development of the SDN architectural approach. Network Function Virtualization, NFV, offers another network architecture concept that decouples the network functions such as network address translation, firewall, intrusion detection, DNS, etc. from proprietary hardware appliances to run in software. It uses standard IT virtualization technologies that run on high-volume servers, switches, and storage devices to virtualize entire classes of network node functions into building blocks that may be connected or chained together to create communication services. NFV and SDN are complementary. They do not depend upon each other. You can do SDN only, NFV only, or SDN and NFV together. Some short background information about the history of NFV. In November 2012, 13 telco operators, including AT&T, BT, German Telecom, Telefonica, etc., have introduced the NFV industry specification groups under organization of ETSI to achieve that general-purpose servers, switches, and storage devices will cover the functions of traditional telecommunication networks. In 2013, ETSI's NFV ISG industry specification group started to implement relevant standardization and to draft NFV architecture for telecom industries. The main benefits of network function virtualization are to reduce the CAPEX by reducing the need to purchase purpose-built hardware, to reduce the OPEX by reducing space, power, and cooling requirements of the equipment, to improve O&M by virtualization, and to provide flexibility by quickly scale up or scale down services to address changing demands of the market. So this subchapter gave an overview about SDN by describing the essential principles of SDN and also providing a short view of NFV, network function virtualization. Thank you for watching.